next speaker is Raghavendra Bhat. He's a freshman at Wright State University, and he's really into mathematics and wants to tell us about some of his conjectures.
Thank you so much for the introduction. Good afternoon, everybody, and I'm really fortunate to have this platform to talk about prime numbers. And I'm from India. I'm doing my freshman year at Wright State University. I'm a math major, and today I would want to share with you some of my prime number conjectures that I came across and I discovered in the last 5 years. So ever since the age of 15, I've been passionate about prime numbers, and I accidentally came up with the Goldbach Conjecture without knowing that it actually existed, and I thought for a few hours that it was my own, but then I realized that it's already known. So I set out on this mission to come up with prime number conjectures that would be original. And I have shared my prime number conjectures with a few mathematicians of various universities in India as well as the US. And my goal in life and my dream is that someday I will meet one number theorist who will be able to help me, approve those things, or maybe make a paper out of it, or whatever that is. So I want to share with you 3 of my conjectures. I have more than 30, but due to lack of time, I will get to share with you only 3 of those, and I've picked 3 that might interest all of you the most. When I say conjectures, I don't know for sure that these things work out because there is no genuine proof. But intuitively, with whatever mathematical knowledge that I've had, I feel that they work out. And I cannot explain why I feel it. It's just a gut feel, but I feel it. And I've verified them on Python. It's a computer programming, so I've just verified it up to 1 billion or 1 trillion. So I know it works out up to some large numbers. But as you know, when we talk about infinity, trillion is just a drop of water in the entire Pacific Ocean. However, since prime numbers deal with probability, I feel that if it works out to 1 trillion, it should probably work out forever. I mean, that's just my beginner level mathematical research thinking. So in the slides, whenever I say the capital letter P, I'm referring to the set of all primes, and Pn is an element of the set of all prime numbers. This is the first conjecture that I want to present before you. It says that every multiple of 6 could be expressed as a sum of a square number and a prime number. Now the Goldbach Conjecture says that every even number is a sum of 2 primes. So this is a slightly less probable of a claim because the density of square numbers is a lot lesser than prime numbers. So we have a lot more prime numbers than square numbers. So for this to work, it's a lot harder than the Goldbach Conjecture. However, it only works for those multiples of 6 that are not squares. So the multiple of 6 cannot be something like 36 or 3600 or something like that. It only works for non-square multiples of 6, and they can all be expressed as a sum of a prime number and a square number. There are a couple of really interesting things here. The first one, so these are the few examples. You can see a small multiple of 6, 24, can be written as 1 plus 23. 1 is our square number, 23 is the prime. And you will notice that this huge number here, which is 18 million something, a multiple of 6, is just the sum of a really small square number and a huge prime number. So as the numbers increase, the square numbers tend to be small, but the prime numbers tend to be really large, which means if somebody is able to come up with some sort of logic as to how to come up with those square numbers, we can easily generate huge prime numbers with just multiples of 6. So it's a very efficient method to generate prime numbers if we have control on those square numbers. So, and for most of these numbers, they can be expressed as a sum of a square and a prime in many different ways. And the interesting thing about this conjecture is that if this happens to be a prime multiple of 6, so it's like 6 times 3 or 6 times 11, then it could be a prime squared plus a prime, not just a natural number squared plus a prime. So it could be a prime number squared plus a prime. So we are dealing with 3 different prime numbers in one conjecture. There's a prime multiple of 6 is a sum of a prime number squared plus p, and it works out for all prime multiples of 6 up to 1 trillion or whatever that is. So that's the first conjecture. The next conjecture that I want to present before you is what I call the 2 to the power conjecture. It's a very, a big claim that I'm making, so it could work 2 ways. This could be something that out of my immaturity I'm making a huge claim and it could turn out to be wrong. But if it does turn out to be true, it could change the way we look at numbers. Because what I'm trying to say is that every odd number could be built using just powers of 2 and primes. So I'm basically saying that so odd number is a kind of numbers that could be generated using all sorts of combinations of powers of 2 and primes. So what I'm saying is that for every odd number, you could represent it as a product of a power of a 2 and a prime, and you add another prime to it. So every odd number is a power of 2 times a prime plus a prime. And the interesting thing is that the power of 2 could be any power of 2 which is smaller than the square root of the odd number. So if I take an odd number like 101, I could write it as a power of 2 times a prime plus a prime for 2, 4, and 8, because 2, 4, and 8 are powers of 2 that are smaller than the square root of 101. And it works for all odd numbers. So multiple ways of representing the odd number using just powers of 2 and primes. So the corollary is that for every power of 2, any odd number that is bigger than its square could be represented as that power of 2 times a prime plus a prime. So if my power of 2 is 64, every odd number greater than 4096 can be written as 64 times a prime plus a prime. So that works for any power of 2. Here are a few examples. 7 can be written as 2 times 2 plus 3, because the power of 2 which is smaller than the square root of 7, 2 is not actually, so 2 is the only power of 2 which is smaller than the square root of 7. For 101, I could write it as 2 times 47 plus 7. But 101 can also be written as 4 times 7 plus 73, because 4 is a square root lesser than square root of 101. And it could also be written as 8 times 5 plus 61. And this could, indirectly refer to the fact that 2 to the power numbers and prime numbers could be building blocks for all odd numbers in the universe. Okay, one more conjecture which I call the complete conjecture, because it deals with all the 4 arithmetic operations. I think I have it on my tie somewhere. Addition, multiplication, subtraction, and division. So what I'm saying is that for every multiple of 6 which is greater than 1000, there exists one special prime number. There exists one special prime number which could be added, subtracted, multiplied, or divided to result in 4 different prime numbers. So if you find that one prime number, you could generate 4 other primes. So when I say multiplication, we have to multiply and add 1, because if you multiply 2 numbers, it cannot be a prime. And when I say division, it's integer division. So I say 10 divided by 3 is 3. So let's have a look at a few examples. If my multiple of 6, which is greater than 1000, is 1002, my prime number is 359. So why is this prime number special to 1002? You could add it to get a prime, that would be 1361. You could subtract it to get a prime. You could multiply and add 1 to get a prime, or you could divide it to get a prime. So you can see a huge example here, 2,433,516, which is a multiple of 6. The unique prime number is 2293, which could be added, subtracted, multiplied, and divided to get a prime. So it really fascinates me that there exists one prime number which could generate 4 other prime numbers. But then, how do you find that one prime number? That's what is my ambition, that someday I should be able to get a control of these conjectures. I want to share a couple of sequences too. These are sequences that very recently came in my mind. As I started my freshman year, I was thinking about all my old conjectures, and I thought that some sequence like this might be really interesting. There are 2 sequences. One is a simple sequence, one is a complex sequence. They are a sequence of square numbers. And the sequence is such that if you add, in the simple sequence, if you add any 2 adjacent squares, you should get a prime number. So you start with 1, which is the smallest square number, and then you come up with the next square number, which will be added to 1 to get a prime. And that is actually 4. So this is the simple sequence. You have 1, 4, 9, 64, and then it just goes on and on and on. So this sequence should never end, because there are infinite squares and there are infinite primes. So if somebody can come up with some sort of a logic as to what is the pattern to generate these squares, then we can also generate primes, because adding any 2 adjacent squares gives a prime. So this goes on. So then 4 plus 9 is 13, 9 plus 64 is 73, and it goes on. And this is the complex sequence, which is similar, but there is an extra condition that we have to follow. Not only should the sum of 2 adjacent numbers be a prime, but if you multiply them and add 1, you should get a prime too. So there are 2 conditions for this sequence to exist. It's not just adding, there's addition as well as multiplication. However, it looks a little similar to the simple sequence. You start with 1, 4, and 9, and 64, and then it changes. So you can notice here, 1 plus 4 is a prime, and 1 times 4 plus 1 is also a prime. 4 plus 9 is a prime. 4 times 9 plus 1 is also a prime. And it works for huge numbers too. So the goal with all of these conjectures is to come up with a strategy to generate prime numbers. That is something that I've always been passionate about. Now, why do I like prime numbers? I do not know, but there's a remarkable coincidence. I was born on March 13th, 1999, and 3 is a prime, 13 is a prime, 1999 is a prime, at 3:47 p.m. in house number 37, and I was the 7th member of the family. So ever since I was a kid, I've always been passionate about prime numbers, because for me, doing work in mathematics should always be trying to do something new. And I found out that prime numbers is this one area where there is very little that is known. Now we do know that given a number, the number of prime numbers up to that number are n upon natural log of n. However, nobody actually knows how to generate primes, nor does anybody know if I show you a large number, you don't know whether it's a prime or not. So my goal is to get more ideas on these prime numbers. Before I finish, I want to share with you one last concept that recently came into my mind of late, and it's a new type of numbers that I've thought of, and I call them Rn numbers because my name is Raghavendra Bhat, so it's Rn numbers. So Rn number is defined as a product of a square number and a prime number. The square number should not be 1, because if it is 1, then it's just the same set of prime numbers. So an Rn number is a product of a square number and a prime number. So I thought, okay, what is so special about this? I mean, it's just a product of a square and a prime. But then I studied them closely, and I did a little bit of, I played around with them a little bit, and I found out that the number of Rn numbers which are smaller than a given number is also n upon natural log of n. It seems to be. I mean, I don't know how to prove that, but it seems to be. And every number which is greater than, I think, 1000 can be represented as a sum of two Rn numbers. So all the conjectures that work for prime numbers also work for these numbers that are product of primes and squares. So I think these numbers might be useful at some point of time. Like, for example, tau is more useful than pi because it is 2 times pi, and 2 pi is used more often than just pi. So I feel Rn numbers could be more useful because people can have control over them. You know how to generate them. You just need a huge square number. You can multiply it to a prime number, you can generate it. So I feel they could be used in the future, and that is probably going to be my grad school research work that I want to do, but I don't know how good that would be, or what is it going to be, and what God has in store for me in my upcoming years in my life. I've just begun this journey in mathematics, so I want to do one of these things, try to come up with some group, ring, or field to do with prime numbers, or try to come up with a technique to do factorization, or crack the RSA cryptography technique, because it's kind of, people feel that it's really weak. So that's what I'm trying to work on. That's it. I'm really thankful to all of you for giving me an opportunity to talk here. That's my email ID, and I recently wrote a book titled Math, a Subtle Language of the Universe when I was in India. So it doesn't talk about prime numbers, but it just talks about various other mathematical concepts. And I sincerely thank my calculus professor, Professor Joe, and also Professor Dan of Wright State. They gave me this opportunity to speak here, and I'm really happy that this was the first conference that I spoke to after coming to the US. Thank you so much. Any questions?
Anybody have any questions for the speaker?
So there are related conjectures with the Goldbach conjecture and others.
Yeah.
The methods of proof for partial results along those lines, are they applicable to your conjectures? Have you tried those?
For the multiple of 6 times?
The first conjectures you were
This
using,
one?
yes. Similar, correct, yes.
Oh, so a Goldbach conjecture has been verified up to 10 to the power 18, but I don't know if it's been proved. There's some sort of an understanding on it, but I do not know if that would work here too. I mean, I wouldn't probably understand the partial results that have been derived on Goldbach conjectures. Maybe someday I will. But these work to 10 to the power 12
Right.
too, and I don't know. I think if the Goldbach conjecture is proved, then maybe many of my conjectures could be proved too, because it deals with similar concepts, getting two numbers to add up to something. However, I feel probability could be a good way to verify this. We know the number of square numbers that are there, smaller than a number, and we know the number of prime numbers that are there, smaller than a number. So it's just about finding, can there exist one pair where a square and a prime can add up to this number? It's just about that. I think it's about probability. However, that's not going to be a very concrete and convincing proof, but I think that's a way to look at it. Any other questions?
Any other questions for the speaker? Let's thank him again.
Thank you so much. Thank you.